Hello.
Hey, how are you?
I'm good. How are you?
Good, thank you. What's new?
So I did part of the MCAT contact diagnostic for Jack Weston. I did the biochem section. I'm still working on chem phys.
Hmm.
Um, so I mean like I did okay. I did get like a 60%, which isn't like crazy high, but
Uh-huh.
um I got to see like what I'm missing, so that's good.
Hmm.
Um I also finally feel like I came up with like a pretty good study regimen for me. I feel like it's just I don't know. I feel like it's been a while since I was in undergrad, so
Yeah.
I just forgot like what how I studied before, but I just remembered like I used to like record myself saying certain things,
Yeah.
like listen to it. So I figure that's like what I'm probably gonna do for most of the information that I don't know right now. So
Hmm.
I definitely feel that's going to make a significant difference. I'm like, damn, like I don't know how I forgot that I was an auditory learner, but
Yeah, I
I'm
was about to say. But yeah, no, I was in that like I took like 5 years off of college before I took the MCAT, so I had to like relearn how to study, which was like a blessing in disguise. I mean, like it takes longer, of course, but it let me learn things again, in like the proper way that I
yeah.
school.
Yeah, no, it's been 5 years since I've been in school too. Yeah. But yeah, no, I'm excited.
Hmm.
So let me see what I wanted to work on. There was this one Chem Phys section question that I didn't necessarily know how to approach.
Is this
How
test or from the content diagnostic?
this is from the practice test.
Okay. Is this full length too?
Mm-hmm. I did notice though, like even though my score isn't like for cars, I only got like
Mm-hmm.
17 questions wrong, and I'm just like, hey, I from my point of view, I feel like that's an improvement. Like
Uh,
even if I got like a 124,
yeah,
I feel like I was definitely getting way more questions wrong in cars than I am now. So I'm getting a little bit better at cars.
it's good.
Yeah. Oh no, I was starting at this one. Are you doing anything for Memorial Day weekend?
Nope. Are you?
I don't know. I'm like debating. Like my one friend like invited me to a barbecue and I'm like, oh, I feel like that'll be fun, but
Yeah.
uh
Give you a
so
good like break from MCAT stuff.
okay, fine. I was like, oh, free food, you know.
Yeah.
Okay, so I would think it was this one, passage number 7. Let me share my screen. Share. Okay, so let me see. So, okay, but let me change it to the what do you call it? Jack Weston.
Yeah, you have to do it like yeah.
Click.
Hmm.
So I'm like, oh, I thought that this passage would be easy because it's like so short, but um so the hydrated copper ion CuH2O4 is converted into a complex ion copper NH3 in aqueous ammonia NH3. The formation of CuNH3 4 takes place in a stepwise manner, with one water molecule being replaced by an ammonia molecule in each step. The sum of all individual steps gives the overall transformation shown in equation 1. And then the formation constant, I feel like I'll just highlight that. And then the value of the formation constant is 5.6 times 10 to the 11th at 25 degrees Celsius.
Hmm. Yeah, so a good amount of this could be a content thing about coordination complex, which could also be called like a dative bond, but it's essentially when you have some transition metal that is that forms non-covalent, well, I guess we can call them like coordinate covalent bonds with the water, but it's typically like something like this, where we could have like water forming these types of bonds that are so like I think I mentioned before how like a covalent bond we typically draw as a line,
Mhm. Yeah.
like intermolecular bonds like hydrogen bonds or ion bonds or anything like that. Um, we typically draw like anything but a line, like either dashes or dotted line or something like that. And also like if you have a covalent bond, so like for instance, like water, the bond within water would look like this, and that also means that the compound has a neutral, which means no charge because like so basically like the oxygen here should be 2 minus, and then each of the hydrogens will be plus 1, and since we have 2 we have plus 2, and so the overall molecule is neutral. that's like that's like covalent bonds. Now for a coordinate covalent bond, it does not make the molecule neutral anymore because you could see that even though we still have a coordination complex here, it still has a plus 2 charge. So that's what you're going to see for coordinate covalent bonds. You'll see a central atom that's like a transition metal, and it'll be complexed by some type of molecule like H2O or ammonia. And also the molecule that it's complexed with don't so like in a regular covalent bond, each atom brings its own electron. So it's like the sharing of electrons, but in a coordinate covalent bond, the electron pair comes from just one of those molecules. So like, in this case, it's from the H2O that brings in um, a lone pair to bond to donate essentially. Uh,
Mhm.
and when it's converted into this one, this is also, a coordination complex. You just have the H2O molecules replaced with ammonia, and ammonia also has a lone pair that it can donate. So then this can just turn into so like and they say that it's happening one at a time, like one water molecule being replaced by an ammonia molecule in each step. So like the first step would just involve like one of these water molecules being replaced with an ammonia.
Mhm.
And the next step, the next one will be replaced. So it's going to be like 4 steps total to get this. Um, and you can see how in this equation it's like we have the first version, which is just complex with water, and we add 4 ammonia um, molecules to that, and then it just replaces it. Like this is the overall reaction, but it's going to be one at a time. And the water gets kind of kicked out. And yeah, so this is the topic of coordination chemistry or coordination complexes. It could also be called dative. And And yeah, so what it is essentially is, or how to recognize it is typically there will be a transition metal like this, some molecules that donate electron pairs, some number of them, and then you'll see a closed, it'll be enclosed in a bracket with a charge outside of that bracket.
Okay.
So this would look more like this, but it's actually the copper that has the +2 charge still.
Mm-hmm.
But yeah, it could be drawn like in terms of brackets. So this is a just like for the most part, um, like a content thing of just knowing the coordination stuff. Because like I've gone over this passage with a lot of people, and usually it's like just like a content thing. But yep, that's pretty much the content aspect of it. So yeah, let's try this question out. So yeah, what do we do here?
Um, so part of me feels like it's a non-spontaneous process with a positive delta G. I feel like I got this wrong in the exam because I think I was thinking about it um from a different point of view. But now I feel like because you're adding one um ammonia molecule at a time, like that's why I think it would be non-spontaneous.
Um, so nothing like that will help us in figuring if something is spontaneous or not, because we need to figure out, well, what do we need to figure out if something is spontaneous or not?
Um, you need the delta H and the entropy.
So those things can come in to an equation for something. So so those can play a part, but what's like ultimately the thing that determines like what's one value that if it's negative or positive, it can tell you if it's spontaneous or not?
Oh, delta G.
Yes. So now the first thing we can do here is so okay, do you know if like what the value of delta G would be if it's spontaneous or not spontaneous?
Yes, it would be negative if it was spontaneous and positive if it was non-spontaneous.
Good. So we could actually eliminate some choices right off the bat with that type of thing, right?
Through A and this one. So see, yeah, between B or C.
Good. So so that's just, that's like a way of eliminating choices based on like I don't mean like the psych-social term, but like internal validity, like within the statement, like even without looking at anything, we know that A and D cannot be true. So now we need to figure out if the delta G is negative or positive. So we can't figure that out from like just looking at the you know the steps and stuff like that. Like you will need experimental like values. So you named one of the equations for delta G. Tell me what that was again.
That's delta G equals delta H minus T times delta S. But there is another one where it's like delta G equals um R RT no, or it's like LN no, or yeah, RTKQ or something like that. Yeah, okay, LNKEQ.
Yep, and this there will be a negative there.
Yes.
Um, and there's one more that
Yeah, that's for the that one is delta G equals NFE, and that's for the redox reaction.
yep. So that's also going to have a negative in
Hmm.
there. Now, okay, now what is the delta eight? Like, what is that?
The enthalpy is like whether or not you have heat. being absorbed by the reaction or if it's being released by the reaction.
Okay. So like if it's absorbed, like what would delta H be?
If heat is absorbed, um, delta H would be negative.
It'll be positive.
Positive, my bad.
Because so think about the delta H. So like that would be final minus initial.
Mhm.
And so if we have heat being added to the system, we would think of that as possibly being like a reactant, right? Like if for this equation one here, if I had heat added to the system, I could just write it as a reactant, right?
Yeah.
And so if I write it as a reactant, it would be on the left side and not on the right side because the right side is the form of it with the heat absorbed already. So the overall heat is higher for the products than the reactants, right?
Hmm.
So that means the final enthalpy should be larger than the initial enthalpy, right?
Yeah.
And that means that this change in enthalpy is going to be positive, right?
Yes.
So so it's good to like kind of like deconstruct things to gain a better understanding of it. So because like on one hand you can just like memorize it, but I also want you to be able to figure it out without that because then you can think about it logically like okay if delta H so if we're talking about it and by the way what is it what type of reaction or what is it called when the heat is added as a reactant?
That's exergonic.
Kind of maybe.
Exothermic.
So
Oh,
closer. Okay.
sorry, endergonic.
Oh, that was the first thing you said, I think.
Oh, okay.
But if we are adding something, we're putting it in. So it will be endo or exo.
Um, endo?
Okay? Because the in part, right?
Hmm.
Endo means inside, exo means outside, right?
Yeah.
And then the gonic versus thermic. So the
Oh,
so the gonic is going to be just think of it as okay, it starts with the G and so does delta G. So the delta G will be the gonic stuff, but the thermic stuff is going to be for delta H.
that makes
So
sense. You're
mhm.
dealing with heat. Okay. I see. Okay. Yes.
Yeah, I mean like it's it's kind of it's kind of weird because it's like because the enthalpy we can think of as heat energy, but also we could think of it as bond energy, like within the bonds whenever you break a bond. So it could be a little confusing that way. But yeah, so if your delta H is positive, it's endothermic, and you could think of that as heat being added to the system. So you could think of heat being a reactant. And the opposite would be if heat is released by the system. So instead of this, if it's at a as a product, right? That means that the
It's
product side heat is released, which means that the final enthalpy is smaller than the initial. And that's why the delta H in that case would be negative. Because in that case, the initial enthalpy will be greater than the final, right? Because we are losing heat.
I see. Yeah.
So if you're subtracting it by a larger number, this will then become negative. And then that will be um, exothermic, which means it releases heat. Okay. So that's that. T is temperature, and we use Kelvin for temperature. Why do you think we use Kelvin? Like, what's the, like, we know that we're not going to use Fahrenheit, but we can have Celsius and Kelvin, but like, what's the utility of using Kelvin?
Um, mm, yeah, I'm honestly not quite sure. I just
So let's think about, okay, what's the lowest possible temperature or okay, so yeah, okay. What's like the lowest temperature you can have in Kelvin?
um I
So,
guess that, oh, if it's zero Celsius, then it would be 273
okay. Now,
Kelvin.
if you go smaller for Celsius, you go into the what territory?
The negatives.
Okay. But for the Kelvins, you won't ever have anything negative, right? And
Yeah.
that plays a big role because look, if we're subtracting this number, right? And if we use temperature as Celsius and we have like negative 20 degrees Celsius, this equation then turns into like delta H minus a negative value, which means the overall value goes up, right?
Hmm. Yeah.
So, so I mean, it's I don't think they're gonna ask you that, but it's good to like ask that kind of question, like, okay, why do we even like? There's Fahrenheit, there's Celsius, there's Kelvin. Like we use Fahrenheit like in America. Uh, Everyone else uses Celsius, so it's like it's not that intuitive. It's like 25 Celsius. Like what is that, right? And then
Yeah.
Kelvin on top of that. But yeah, it's simply because 0 Kelvin is considered absolute zero, which is like the lowest temperature anything can be. Um, so okay, good, good, good. And then yeah, delta S is entropy. Now for the delta G, which tells us the Gibbs free energy, if the delta G was negative, that would be exergonic. Okay.
Mhm.
And if it was positive, it would be endergonic. Okay. All right. Now, so we talked about this formula. This formula comes in when you're dealing with like cell potentials, like when you're given like a redox reaction, as you said. Um, N is just like the number of electrons. F is a constant, Faraday's constant. And the negative is there because if the like N and F can't be negative, but E cell, the cell potential, can be negative. It can be positive as well. So if it's positive, the overall number becomes negative because of the negative, right? So if cell potential is positive, delta G is negative, meaning it's spontaneous.
Hmm.
And then vice versa for if it was negative, you would have negative of a negative, which is positive, which is um, endergonic or non-spontaneous. Now here, over here, they kind of like have been trying to like use this vague kind of word here to kind of maybe throw us off. But we see here that this is a K term, right?
Yeah.
So So we see that, and anything that has a capital K, right? It's all derived from something called the law of mass action, which is essentially products over reactants. And for and it's so the brackets mean, I guess that could be a bit confusing because we have brackets here too. But in general, brackets in chemistry, like for a K equation thing, like would be like, let's say I just had like, I don't know, ammonia. Like if it's in brackets, it means the concentration, so the molarity, right?
Yeah.
And also whatever in the chemical equation, the balanced chemical equation, whatever this coefficient is, gets turned into an exponent. Okay?
Yeah, gotcha. But the
And yep.
two pluses, those are not exponents, right? That's just like the charge of the copper.
Yeah, correct. Uh,
Gotcha.
because yeah, they're in superscripts for the equation. Um, and they'll stay, I guess, superscripts in here because that's like the formula for that molecule. But you can see like the 4 here is not a superscript, and that does get turned into one
Gotcha.
outside of the bracket. Now the last thing is, since we are since all of these bracket terms are concentrations, we can't include pure substances. So, so like that's something that they say a lot. They just say like, okay, you don't include like liquids or solids, but I want you to see it as you don't include pure substances because if a substance is pure, its concentration value will basically just be one or like like 100%, which doesn't change anything. So that's why in this K formula we don't have the 4, molecules of H2O because it's yes, because it is a liquid, and it's true you don't include liquids, you don't include solids, but the reason for that is because they're pure substances. So a lot of times you might be dealing with KSP.
Yeah.
And so that's same type of thing with the Ks, but that's when you have something that's a solid, like dissolve in some type of solvent. And so if you're doing something with a KSP, the reactant that's a solid, you're not going to include the solids or liquids. So for a KSP, you're not going to have anything in the reactant. So you're not going to have a denominator. Like if it was like CaCO3 turns into Ca2 plus aqueous plus CO3 2 minus aqueous. Like I guess I'll write it aqueous solid. Your KSP is just going to be like Ca2 plus concentration times CO3 2 minus concentration, and that's it. Because on the bottom, you would normally put the reactant, but since our reactant is a solid, we don't put that, so we're not going to put anything in the denominator. Okay, so, all right, so we talked about a lot of stuff, so now this is what we're going to hone in on because it actually has a value inside of it that we can use. Now yeah, we're going to say something?
Yeah, I just thought that it was KEQ specifically for this equation. Is it that I you could use just any type of K?
You could use any type of K, and also, so sometimes they would write a Q instead of a K. Have
Oh, okay.
you ever seen that?
No.
So like K, it's basically the same thing as K, but KEQ is particularly well at equilibrium, right?
Hmm.
And so if you do something that's not at equilibrium, we can just call it a reaction quotient with a Q in it.
Hmm.
Um, and that's just like if you are so here, let me So this reaction here is at equilibrium, but let's say that we added some more ammonia, right? Then this will no longer be at equilibrium, right? And you could then express it as Q, but it'll through Le Chatelier's principle,
Yeah.
the reaction will move in whichever direction it needs to move to reestablish equilibrium. So if I added ammonia, it'll push the reaction forward until it reestablishes equilibrium. Okay? Okay. Now, for this equation, you want to see, so I'm going to use blue. So you want to see that, so this type of thing you want to see is like, okay, so for like K, let's say that it's, okay, okay, since K would be like react or products over reactants, if the products are equal to the reactants, this will be equal to 1, right?
Hmm.
And let's say that your you have a higher amount of products, this K term, so and here, I'll put this also like products over reactants. So if you had a larger number of products than reactants, the K term now becomes greater than 1.
Yeah.
And then if you have a larger number of reactants, this K term becomes less than 1, right?
Hmm.
Okay. Now, it's useful to see things this way, just like for like delta H and delta G and stuff. I talked about it being like either less than 0, greater than 0, and then of course it's if it is equal to 0. So being able to see uh numbers in that type of way, like okay, negative or positive or 0, and with KEQ equal to 1, greater than 1, less than 1, you can then use that to ascertain the log of it. So for instance, if we had, and it doesn't really matter if it's ln, which is natural log, or log, like log, but we could say that ln of k, like, okay, let's say when k is equal to 1, the what do you think the log of that would be?
Mm. I I think it would be positive.
So we could uh we could think about it like this. So here, let me do this with a base 10, and let's say this is x, and then let's say this is a. So if you think about 10, the base, to the power of a is equal to x. 10 to the power of a is equal to x. So that's how you can do logs like this. So like for instance, let's say we have log of 100 is equal to a. That means we would do 10 to the power of a is equal to 100, right?
Yeah.
So a would be what in this case?
Um, two.
Mm-hmm. Good. So let's say now we have um So now this time we're going to do log of 1. So it'll be 10 to the power of A is equal to 1. What could A be? So I'll write this in red here. Or, so anything, any number, let's just say whatever, 10, any number to the power of 0 equals 1. Okay? So this would be 10 to the power of 0 is equal to 1, right? Good. And so here, if k is equal to 1, ln or log of 1 is 0, right?
Yeah.
Okay. Now, if you did the log of something that was, let's say, um, log base 10 of like 0.01,
It'd be negative
yeah,
three,
good.
two.
So if your KEQ is less than 1, our log of K would be negative, right?
Hmm.
And then if our KEQ was greater than 1, our log of K would be positive, right?
Yeah.
So good. So it's good to be able to see ratios because KEQ is a ratio of product over reactant. It's good to be able to think of ratios as uh, falling under three, I guess, possibilities. Either the product concentration is equal to the reactant concentration at which it'll be 1, or if the numerator is larger than the denominator, it'll be greater than 1. If the denominator is larger than the numerator, it'll be less than 1. Okay? So now that we have that, in this reaction here, we our K value, we could just use this one here. All right.
Okay.
And yep,
I said, okay, that makes sense.
yep. And then they give us the value, and it's a positive number, right?
Hmm.
And the log of a positive number will be,
A greater than zero.
yep, meaning positive, right?
Yeah, yeah, positive. And
So
then,
this lnk term is positive, but since we have this negative sign in the at the beginning, the overall delta G is negative then, right?
okay.
So
Dang.
would be B, right?
Hmm.
Okay. So that was good. We covered a lot just in this question. Um so so yeah, so like overall, think about you did good in remembering like the three delta G equations. And then it's just a matter of like, okay, which one do I use? Like, okay, there's no cell potential value that they're giving us. There's no like enthalpy or, entropy delta S value that they're giving us. They are giving us temperature and but still we don't have enough to do this. And then here we can do this. Um, and they're giving us temperature, sure. And R is something we should know, the constant for it. Um, but we don't even need to really do that because it's not asking us for like the specific delta G value or anything like that. It's just asking us if it's spontaneous or not. And that's all we need. Yep.
Gotcha. I feel like, yeah, I tend to like shy away from the negative RT LNK reaction just because I'm like
Hmm.
the natural logs just scare me, but I feel like if I'm just looking at natural logs like regular logs, then it'll probably be fine.
Yep. Yeah. So when it comes to logs, just remember that it, that if you're taking the log of so okay, if you're taking a log of one, it's zero. If it's a log of something greater than one, it's greater than zero. If it's a log of something less than one, it's less than zero. So like basically like yeah. So like just remember like let's say log of x, if x is equal to zero, log of x is equal to one. If x is greater than zero, log of x is, oh, sorry, if it's greater than one, I should have said. Here, I'm just gonna clear this so I can make it unambiguous. So let's see. So if x is equal to 1, log of x is 0. If x is greater than 1, log of x will be greater than 0, aka positive. If x is less than 1, log of x will be less than 0, meaning negative. Okay. And then this x stuff plays a role. So I'm going to write one more thing and then you could take another
Oh,
screenshot. That's okay. So now when it comes to ratios, because like this looks really simple, but how do we get that from like the k thing here? So like if you have, I guess I'll just write k. So like, let's see, if k is 1, log of k is going to be 0. If k is greater than 1, log of k is going to be greater than 0. If k is less than 1, log of k is less than 0. So pretty much that. And like also in parentheses, maybe I'll write um, products concentration is equal to reactant concentration, product concentration larger than reactant concentration, and product concentration is less than reactant concentration. So, yep,
yes, that makes sense.
yep. You could take a, yeah, good.
Nice. Okay. Um,
Mhm.
oh yeah, I feel like I got this one, but let me just check it. In the stepwise formation of Cu NH₃ from Cu H₂O4, which of the following ions would follow in the second step? So that's like, yeah, because it's one at a time, so it would just be two and two.
Mhm.
Yeah, so I think, yeah.
So, show me which of these choices is the first step. What happened after the first step?
Okay. Um, so after the first step, okay, yeah, after the first step, the hydrated copper ion loses one H₂O and gains one NH₃. So it would be this one would be after the first step.
Good. And you already got after the second step, after the third step.
After the third step, it would have two and two. So then it would have one H₂O
Oh, I
and
guess it's not. Yeah, they don't have that as an option. Okay. But yeah, good job. So wait, which one did you choose?
it would be this one, right? For the second step.
Oh, so oh yeah, yeah, yeah. Because this one
Okay,
has three. Got it.
let me just
Mhm.
okay.
And this is what I was saying about the content thing.
Yes, so this is coordinate
Mm.
Ionic. Coordinate covalent.
Yeah. So ionic is something we don't see that much on the MCAT, but like if you kind of remember back to like Gen Chem, like it's basically when you have a bond between like a metal, not like a transition metal, but like a regular like first two groups, like something like sodium chloride is an example
Yeah.
of an ionic bond. You have group one or group two metal, and then like in this case, like a halogen, and like this can break or dissociate in water. So like an
Mhm.
ionic bond, like if we were to draw like the bond, like it could still be like a straight line like this, but you're typically not going to see it that way. Um, so that's ionic. Covalent, we talked about that. That's like the general bond that exists as like drawn as like a straight line. Um, and it results in the molecule being neutral. And then this is coordinate covalent and it's its own thing. And you're going to have uh, a transition metal and then several things around it that can donate electrons. But the ultimate thing is going to still be in brackets. Um, and there will be a non-neutral, non-zero charge. So it'll be typically like a positive charge because the transition metal is going to be more likely to lose electrons and gain. But yeah, when you see something in this form, like let's say I wrote like A, X, N, and then let's say like I don't know, some number like N plus or something like that. Like that's typically the form that you'll see something like this in, like a coordinate covalent complex like that. Um, Whereas anything else would just be like, without the brackets. If anything else is with the brackets, we consider that to be the molarity. But yeah, this is just coordinate covalent.
Right. And then just like so the ionic bonds have like the straight lines, like they wouldn't have dashed lines at all.
Yeah, yeah. Now, you're typically not going to see like regular ionic bonds in on the MCAT because you'll just see them as being like salts that dissociate.
Hmm.
But you could have ionic interactions, which are closer to like intermolecular bonds than full-fledged covalent bonds. So a good example would be like I guess like a carboxylic acid that has lost its protons from like one amino acid and the NH₃ plus, and so there's charges. So we can call this like um electrostatic interactions. We can call it like that. Yeah.
Gotcha. Okay, that makes sense. Like, because yeah, I feel like whenever I think ionic bonds, I'm always thinking of like the salts,
Yep.
like yeah. So
That is what mostly all the ionic bonds will be like. Yeah.
gotcha. All right. Consider the reaction shown in equation one at equilibrium. Would the concentration of copper ammonium 4 increase if the equilibrium were disturbed by adding hydrochloric acid? So I guess like um this is not I feel like I've been thinking about Le Chatelier's principle a lot recently just to try and like get it down. So I thought it would be kind of like this, but I mean I still got it wrong. 'Cause I guess I was trying to figure out like how the water molecule would tie into the reaction if you're adding, because I feel like adding hydrochloric acid, isn't that just basically like adding hydrogens?
So when you say adding hydrogens, tell me more.
Um, like I like I feel like with the hydrochloric acid, because it's a strong acid, the hydrogens are more likely to dissociate.
So when you say hydrogen, tell me, like, if you wrote it down, like, what would you write? Like, would
Um,
it be this?
H plus.
Yeah. Okay. Good. All right. So, okay. So now this could also be perhaps a bit of a content related thing, but okay. So we're being asked, okay, what will happen to the equilibrium if we added hydrochloric acid, right?
Hmm.
And yeah, if you add hydrochloric acid, it's essentially adding protons like this. Um, and hydrogen, normally has, one electron around it and a proton in the nucleus, right? But if it loses the electron, it's just a proton.
Hmm.
And so that's one of our definitions of acids, things that donate protons. So now in order for this to play a significant role, there must be something in the equation that now, since all of the choices involve a shift, we know that a reaction is actually going to be like taking place. And if we're adding an acid, then there must be some type of base already in there. Because so yeah, if you add an acid, you are adding H pluses or protons. Um, but I guess you can think about it like what happens to those protons? Like, because if there's protons added here and we should still have them, as products, unless something behaves like a base. And if something behaves like a base, it could be a proton acceptor.
Right. But I guess I'm just confused. Oh, you know what? I think that the ammonia could
Mhm.
act as a base. I think it could take on another hydrogen.
Yep. Because we know that from like the Zwitter ion, right? We know that I kind of wrote like I drew like the carboxylic acid without the proton negative, and then I drew like NH₃ plus.
Yeah.
So yeah, ammonia is a weak base. So maybe make like a note of that just to remember. But also just think about, okay, what can ammonia turn into? It can turn into ammonium,
Hmm.
this, right? With a positive charge. So ammonia is a weak base, and that can now accept the protons that hydrochloric acid is donating. So we see ammonia in for the equation one here on the left. And if you added hydrochloric acid, what'll happen to that to the amount of ammonia?
It'll increase. So would it continue to be on the left?
So this would that increase?
No.
Because it would turn into this, right?
Yeah. So would it just be like a new product?
Uh, you could think of it as less of that reactant.
Oh, okay. Oh, yeah, that makes sense. That makes sense.
Mhm.
So if there's less of that reactant, then I guess the equation would still go to the left. Yeah.
Yep. So, okay, we could eliminate, oops, not that one. We could eliminate these, right?
Hmm.
They'll say shift to the right. Now, what do we need to find out?
If whether or not the equilibrium is well, I feel like it would
So we know the second part, right?
Hmm.
So the first part though is related to what in what they're asking.
Oh, it's asking about the concentration. My bad. I thought it was like asking about the equilibrium. The concentration of Cu. Okay, would it increase? No, I don't think that would increase.
Mhm.
Yeah. So
Good,
B.
right? Because so like yeah, if this because they're asking about the product, right? And if we have a shift to the left, we're shifting towards the reactants. So this amount of product is going to be less so.
Yeah,
There you go.
that's- that makes sense.
Hmm.
Right. I don't know why. I forgot about ammonia. I was like, water?
Hmm.
Um,
Yeah, this is another just like a content thing, um but we could actually probably figure this out even without the content stuff by eliminating stuff. Like for instance, over here, what do you think about A?
yeah, that doesn't make sense.
So what would the oxidation number of copper be?
Uh, 2 plus.
Hmm. Good.
Um,
So it can't be that, and this mentions it, can't be that.
but I guess I just didn't know what the coordination
Yeah,
number.
yeah. That's usually the case with this passage. So now you know. So uh yeah, so this entire thing is called, and they try very hard to like not give you hints here because they're just saying complex here. They're not
Mm-hmm.
saying coordination. Um so yeah, so it's up to us to recognize that as coordination complex, and therefore this number would represent the coordination number.
Okay,
Hmm.
I just thought that 4 meant like the amount of nitrogen ammonia is being added.
Hmm.
But so I guess like okay, so a coordination number is that literally it like the amount of
Yeah,
um
the amount of so let's say you're starting off with the copper ion
mhm.
with a 2 plus charge. The complex is going to be, or rather, the coordination number is going to be how many um ligands can form coordinate covalent bonds with that molecule.
Oh, okay. LOL. That's fun.
Hmm.
So I guess it should just be
Hmm.
all right, goofy. Um
Okay.
oh yeah, why does NH3 displace H2O in the formation of Cu NH3 for 2 plus? Um
Tell me about Roman numeral one.
yeah, Rome 1 isn't right.
So tell me why.
It has the same amount of electrons, lone pairs.
Does it?
Yeah, O2 H2O has 2 lone pairs. No, it just has 1 lone pair, and then NH3 has 1 lone pair as well.
So like, how many valence electrons does oxygen have?
Uh, 6.
Okay. So if it's using two,
Oh, it's 4. My bad. Yeah.
so
I mean,
that would be how many lone pairs?
2 lone pairs.
Yep. So that's why, because if you think about it, right, like if we didn't have these, this should just be a linear shape, right?
Yeah.
But since we have two lone pairs cause more repulsion than regular atoms. So these lone pairs push these hydrogens closer together, and that results in this bent. molecule. But yeah. Um, and then how many lone pairs does nitrogen or NH3 have?
Just one.
Okay. And what would its shape look like?
Isn't NH3 not trigonal planar?
Okay. Close though.
Look at it. Oh, um, tetrahedral.
So that would be like something uh that could have a bond to four things.
Oh, okay. Four things. My bad.
You are on the right track though, because it's like as if it has bonds to four things, but it's really just bonds to three things and then a lone pair.
Oh my God, I'm trying to figure out like what's like, because yeah, there's linear,
Mhm.
there's like bent, there's trigonoplanar. Oh, pyramidal.
Yep. Yep. Yep.
Yeah.
And so I was gonna ask like if you've ever been on like in like a subway or like I usually think about it when I think of the subway turnstile.
Hmm.
It's like this, and it's like you push that. But yeah, basically it's something like this. Well, or rather, I can draw like a triangle. It's like if you take a pyramid, like the pyramids in Egypt, and you just because the pyramids in Egypt have a base of four, like a square, right?
Hmm.
But if you make the base of the pyramid a triangle, and then you make your pyramid, that'll get you your trigonal pyramidal shape. So the N here, an H here, an H here, an H here, and then the lone pair here. Yep. So Roman numeral one, is this correct?
No.
Yeah.
So then it would probably just be C.
So
Um,
tell me about Roman numeral two.
so a Lewis base is something that readily accepts hydrogens.
So
Um,
we can think about the different definitions. So like if we're just talking about a base, we're going to default to the Brønsted-Lowry definition of a base accepts protons and a Brønsted-Lowry acid donates protons. But when we're talking about Lewis, the Lewis definition, it's actually more so like the definition that we use in organic chem, where a Lewis base is an electron pair donor.
okay.
And a
Electron.
Lewis acid will be an electron pair acceptor. And since I said that in a coordination complex, two electrons are coming from the other ligand. Like it's not like the copper is donating anything. They're both coming from the ligand, either H₂O or NH3. So if the electrons are coming from a ligand, then the ligand is going to be classified as a Lewis base. And then why does NH3 displace H₂O? It could be a stronger Lewis base, which means it wants to donate its electrons more than water does.
Yeah.
So that's true. And then Roman numeral three, if it's a stronger Lewis base, then Roman numeral three must be the case, right?
Yeah.
So there you go.
Yes, makes sense.
Mhm.
Okay, so now I'm like, I know what I need to work on.
Yes, for this, I would just say that um so just like the coordinate covalent bond stuff, know that. Um, remember that ammonia can be considered a weak base. Um, and when I say a weak base, I mean like the Brønsted-Lowry definition of accepting a proton. Like I should also say that because there's the Arrhenius definition, the Brønsted-Lowry definition, and the Lewis definition. Why do you think I'm drawing it like in these circles?
I feel like these are the ones that are like most applied.
So the circles mean that, so like for instance, the Arrhenius acid is one that produces hydronium ion.
Mm-hmm.
And the Arrhenius base is one that produces OH or hydroxide ions.
Yes.
Brønsted-Lowry acid donates protons. Brønsted-Lowry base accepts protons. This means that every Arrhenius acid or base can be still a Brønsted-Lowry acid or base. But you could have Brønsted-Lowry acids and bases that are not in the Arrhenius definition,
Oh, okay.
right? So a perfect example would be, well, let's start with how about just water? Like water can be like considered a base and an acid. So like if it turned into an acid, it would turn into hydronium. So I could say, okay, water can be an Arrhenius definition. And here we also see that it's gaining a proton. So water could also be a Brønsted-Lowry definition, right? Now, how about NH3? Well, we know NH3 can accept a proton to turn into NH4 plus. So it fulfills the Brønsted-Lowry definition, but it's not making hydronium.
Mm.
So it's not an Arrhenius definition. So that's what these mean. And then the Lewis encompasses everything, meaning you could have a Brønsted-Lowry acid or base that is always going to be considered a Lewis acid or base, but you could have Lewis acids and bases that are not Brønsted-Lowry acids and bases. So an example of this could be, let's see, trying to think of like a nucleophile that's common. Yeah, maybe like, I don't know, like an alcohol. Like an alcohol can act as a nucleophile, which would make it a Lewis base, and it can attack like a carbonyl group. Like if you had this with a leaving group here and ROH, this can attack that, push this over, push this here, push the leaving group out, and then you would end up with that. So Lewis definition is particularly for like organic chem reactions, but you see that this alcohol group is not gaining like or sorry, is not losing a proton.
Mm.
I'm sorry, is not gaining a proton, but it is donating an electron pair. When something is a nucleophile, by the way, like that's what it's doing, it's donating an electron pair. So this could be a Lewis base, but not a Brønsted-Lowry base. So, yep, there you go. So yeah, I would say, yeah, these definitions, knowing the complex, coordination complex stuff, knowing the ammonia as a weak base, um, both Brønsted-Lowry definition and Lewis. And then, oh yeah, and then being able to uh, understand K and how that's product concentration over reactant concentration and how, K, if K is 1, know that the log of K is going to be like 0. If K is greater than 1, what's the log of that? If K is less than 1, what's the log of that?
Gotcha. So for this week, like after I like study through the material, because I definitely am gonna be really drilling this week, should I take AAMC practice test 3, or I noticed that I forgot to take the free unscored version, or should I do the free unscored?
So I want you to finish the Jack Weston content diagnostics, which, well, you're asking if you should take a test on Saturday?
Yeah, or Sunday.
Yeah, so I would say if you could like finish the content diagnostic, the Jack Weston one,
Mhm.
to yeah, then you could take the one on Saturday. But we should meet sometime like later this week to go over questions that you might have from the Jack Weston content diagnostic because like I think at this point we're not going to see too much of a change in your test score until we get through and make sure we know all of the stuff in the content diagnostic.
Gotcha.
So, so yeah, I would say to prioritize that this week, try to
Okay.
get it finished and try to like, for the ones that you got wrong, like see if you can read the solution. If it makes sense, move on. If it doesn't, use whatever resources you want. But yeah, I would get through those and let's try to meet sometime like this week, like later this week if you can, like before you take your test, just so we can go over all of that content stuff because I want you to make sure you understand all the because I don't want you to be losing, points from not knowing the content. Because I feel like for this passage, a lot of the questions could have just been, if you knew the content. That's the case with most people with this passage. So let's make sure we get that content stuff down. Um, and like predominantly for BB and CP, um, like yeah, try to get Psych Soc done too, but BB and CP are going to involve much like kind of tougher concepts that we have to make sure we understand, whereas Psych Soc it's more so like content that you can kind of like memorize. So
Mhm.
I would say prioritize the Jack Weston content diagnostic for this week. Review it as much as you can and make an appointment. I mean, I could make one for you, but um, like, yeah, do you think you can meet later this week?
Yeah, I'd probably be able to meet on Friday.
Okay. How about what time like range works?
Let me see what my schedule looks like. Like, I'll probably just be at the hospital, but I'm just chilling. So let me see. Where's calendar? Oh, damn. Yeah, probably around like 11. Is that okay for you?
Oh yeah, 11 a.m. on
Yeah.
Friday the 30th.
Hmm.
Okay. I'm putting you in. I mean, like, you don't have to do this, but 90 minutes to make sure we get to cover everything.
Yeah, because I mean, I finished the biochem Jack Weston content review, but I do need to finish CP, so.
Yeah, yeah. And yeah, try to like go over it when you're finished. And yeah, the stuff that still doesn't make sense we'll go over. But yeah, I think that'll play the largest role in your test performance. Oh, and then we can talk about, I guess, like which test to take next. Uh,
Okay. Gotcha.
oh,
Yeah, I'm just a
yeah.
little nervous because I feel like I don't have too much time, but it'll be fine.
Let's see, you're still taking it on June 14th?
No, no, I pushed it to the 28th.
Oh, okay, that works.
Okay, you
Yeah,
should.
even more time. That works very well.
Okay, fingers crossed. Yes, because I need a good score. So,
Yeah, so okay, last thing, let me just see. So there's three of the AMC full lengths um that are left for you, right? The unscored three and four.
mhm.
Okay. And then let's see, one, two, three, four. Okay. So I mean, we have room for four. We have three left. So either we will have you do something else for Saturday or Sunday, and then the weeks after AMC.
Okay.
Or we'll just have you like focus on getting the content stuff down. So yeah. I'll make a decision about that like by the time we meet on Friday. But yeah, right now just prioritize the Jack Weston content diagnostics, particularly BB and BB and CP. Um, and we'll meet on Friday to cover that stuff. But
Gotcha.
basically after Friday, we should have seen all of the content. Oh, and then you could use the content tabs in the shared drive. Okay. All right, awesome. So let's see. Today did like 22, should be 117.
Gotcha.
All
All
right.
right.
Take care, okay?
You're welcome. Have a good day.